Hi, this is the second video of the limits of functions in the course of differential calculus. And here I'm going to get into a bit more detail about what limits are. In the previous video, we just talked about the general concept. Now let's get into into more detail here. I have here my super nice function f of x, which is a piecewise function, as you can see from here. It has this structure. It's equal, the f of x will be equal to x squared when x is different from 1 and has the value of 2 when x is equal to 1. You can see it here on the graph here on the right here. It has the structure of an x squared, and only when the x is equal to 1 you can see that the value of this function is displayed here one level up. As you can see here has the value of 2, just displayed here. And okay, let's get to the limit thing. In the previous video we saw how if you get really in the limit is answering this question here. What happens when you get closer and closer to a value? Of course, here when I say u, I'm referring to a function here. And well, the thing is, if you get really close to the one, to this one here, if you get really close to 1 but without touching the 1, you could say you could input, for example, a value of 0.999 here, and the output in the function, the result, and by inputting here the 0.999 will be something really close to the actual value that it should have. It would be in this case 1. You can see it here on the graph here. So if I get really close from the left, I will get really close to this value of 1. It should be here. And if I will get really close now from the right here of the 1, that is to say with a number which is a bit above 1, it could be, for example, a 1.001, I will get as well really close. If I input this 1.0001 in here, we will get really close to the same value of 1. That is to say, how do you write this in calculus? I mean, in pre-calculus in this case, with a proper notation. I'm going to write it in here. For the first one, which is this one, when you get really close from the left of a of value, you write it like this: the limit when x approaches, in this case will be to 1, and as you're getting from the left of the 1, you write it with a super index here as a negative sign here. You write the number and then super index as a negative symbol here, negative sign here, and then you will write here the f of x. I'm just going to write the f of x here as a general statement, and this will be equal to, in this case, as you get really close from the left of the value, you get actually close to the 1. You get here the 1, and now I'm going to write, I'm pretty sure you can just infer how this will be written, the one from the right. It's the limit when x approaches to 1 from the right is written like this, with a super index with a plus here. Instead of a minus from here, you write a plus, and it will be for f of x. And in this case, you can see that when you get really close from the right of the number, you input a value that's just a bit above the value you're trying to figure out, you get actually as well to the 1 here, to 1 here. And now this is a good moment to write the general statement. How do you write this out in how this works, how this limit idea works to so here's the thing. The thing is, if you had the limit when x approaches to a value, I'm not going to write and this 1 anymore. I'm going to write the general statement. It will be when x approaches to a, this to a from the left to a, for f of x, this is equal to the value of L. And now if the limit when x approaches to a from the right for an f of x is, for f of x is equal to L, if these two guys are just equal, if you approach from the left and from the right, to the same value L, which is a general statement, if you approach to a same value, therefore the limit when x approaches to a for f of x is equal to L. This is purely mathematical, but the thing is, the idea behind it, if you get close, if you approach to a number from the right and from the left and you get to the same value, just like here you go to the same 1 and 1 here, that is to say that the limit exists and has the value, in this case will be L. And in this case, for the example here, I'm going to write it in here because I'm running out of space. The limit when x approaches to 1 for f of x will be equal to 1, and that this is for the graph here, for what's depicted here in the graph here, will be just equivalence. Now here is the thing is, this is like the important thing to remember. If you get close to the number from the left and from the right, and you get to the same, and you get closer and closer to the same value, to the same L, that is to say that the limit will be L, and it exists. Now I'm going to move to another example, which we're going to be seeing how this could be changing here. This is just the idea behind, and let's move forward.